recording and we can kick it off. Awesome. Welcome everyone. I'm George and I'm glad to see so many new faces as well as great friends from all around the world. And this is Deep Learning Adventures, a fun and engaging meetup talking about data science, machine learning, and deep learning in general. We've been taking these Kaggle courses, which is our latest fourth adventure as in our timeline. And if you've never heard of them, they're very short, self-contained mini courses. They cover different topics and they're kind of fun actually. So let me share some links with you where you can find us online on Slack as well as all our previously recorded sessions. And I'll start sharing my screen so I can give you a better idea of who we are and what we do. So as I mentioned, you can find us on Meetup under Deep Learning Adventures. You'll see we have a few upcoming events going on. All our sessions, as I mentioned, are recorded. We covered Python, machine learning, data visualization, pandas, feature engineering, some SQL, geospatial analysis, some special topics like micro challenges. And the last one was machine learning explainability. That was a really interesting one. I encourage you to check it out. So for this session for tonight, we're going to take an introduction to natural language processing and using this library called Spacey. For those of you who have joined us previously, we've tackled natural language processing from a deep learning perspective, so where we use TensorFlow and Keras to do text classification, sentiment analysis. We even did special topics on annotating sentiment using corpus from the Big Bang Theory, as well as trying to detect emotions from a corpus of the popular TV show Friends. So we've seen it from the deep learning perspective. Today we're going to see it from, I would say, from machine learning or more like linear model perspective, simpler models than deep learning. Before I go too far, Robert, should we go around the room and just do a quick intro, just to get to know each other better?
Sure, we can do that.
Cool. I'll kick it off.
Did you want to record that or turn that off?
I can pause the recording for that. Fine. Awesome. It was great hearing it from you all. Thank you for sharing a little bit about yourself. You know what your background is and what you're aspiring to learn, and it brings us closer as a community. So thank you for doing that. Cool. Let me continue sharing my screen and we can start. So as I mentioned, today we'll be talking a little bit about natural language processing. And again, this is an introduction using machine learning or linear models. David, thanks for sharing another session that we hosted in the past using deep learning models. Feel free to check it out later on. So for this session, we have 3 units. I'll be covering the first 2 and David will cover the third one.
I was just going to interrupt before we start to plug our upcoming Coursera NLP adventure next year sometime.
Go for it.
So come back in February and March is probably when we'll be working on that course.
Awesome. Yep. Looking forward to that.
Robert, what topic is that going to be?
The natural language processing specialization from Coursera.
Yeah, as we get closer to Feb, we'll share more information on it. But yeah, it's a new, I would say, specialization from Coursera. Cool. Any other plugins, David, Robert? Love it. Awesome. All right. So this first session really talks a little bit about data format. So far we've seen, if you joined us in the past, we've seen time series, we've seen data structured in tables, we've seen data structured as images, audio data, which we use to transcribe or we use to do some kind of frequency analysis and convert them to structured data. But basically data can come into different formats, but text is really one of the formats that contains a lot of information. Think about it, we've been using text since millennia for now. So it's one of the richest data formats for us that we can extract information out of. So in this tutorial here about NLP, natural language processing, we'll be using this library called Spacey, and we'll be going over that a little bit. But this library is really, really powerful, really useful. It both supports machine learning and deep learning models. You can do things like some basic text processing. You can detect the lemma of a word, basically where the word comes from. You can detect stop words. You can do pattern matching, ignoring cases and things like that. So typical text pre-processing steps, I would say. On top of that, you can also build what is called pipeline and models that you can train them to detect, for example, sentiment, or you can detect you can train them to detect maybe if this email is good or bad, spam or ham, as it's called in the literature. You can maybe train it to look at reviews from restaurants and see if the review is positive or negative or neutral, and so forth. And in the last section that David will cover, you can also look at how better can you represent text in a higher dimensional space in a way that similar words in English or another language, say Spanish, are also the relationship and their meaning is somehow preserved when you represent them in a higher dimensional space as vectors. So that's the topic of word embeddings. This course requires a little bit of an introduction to machine learning because we'll be building models here. If you've taken the Coursera mini courses in the past, and if you've taken this intro to ML or even the intermediate one, then you're in great shape. Otherwise, I'll try and introduce us to any models, as you'll see, and hopefully, especially the first one, should be something relatively easy for us to get familiar with. Cool. So this library Spacey that we'll be talking about, and let's look at the documentation real quick. It's a very well-written library. It supports, as I mentioned, machine learning and deep learning models. It's very easy to install. You can do things like tokenization, where you can break apart a sentence into different words. You can do what is called named entity recognition, where you can specify if this is a noun, a verb, or you can say this is a company, or this is a country, or this is a person. You can basically break apart each word and also assign some kind of a meaning to each word. It supports a lot of language, so it supports, as of now, 61 plus languages. So it's good to see that level of support. It has what is called pre-trained word vectors, and these are really expensive to train, so you can simply import them and use them in your model. It also supports deep learning models as well, some great visualizers, and it's supposed to be used in production as well. So it's not just something that you can build on locally on your machine. It's used by a lot of companies, and the tutorials are very well put together. They also have some video tutorials. They have this metric here, this table that they used to compare with models back in 2017 and 2015. I'm not sure how this table looks like now with newer platforms, but back in 2017, when it was written in Python and Cython, which is C implementation of Python, it used to, it achieved pretty good accuracy on some standard benchmarks. So going back to our first tutorial, we'll be working with this library Spacey, so we will be importing it. And this is a Kaggle notebook. You don't need to install anything. If you use Google Colab, I'm not sure if Spacey comes built in installed. So worst case, you might just have to do pip install Spacey. I haven't tried it in Colab yet. Then the next thing would do is load what is called the basic English language model. You can load other languages as well. In this case, we're loading the English language model. And that gives us this object NLP that allows us to do a lot of cool things. And let's look at some examples. So let's say we have a text here. Tea is healthy and calming, don't you think? That's basically one sentence for us. When we call this object NLP with this sentence as input, we're basically processing or tokenizing it and returning this new object called document. And let's take a closer look at how that document is structured. So it looks like it's some kind of iterable, let's say a list. And if we print each token or each part of this document, you'll see that It looks as expected. It is healthy and calming. Each punctuation is a separate token, so commas, periods is also a separate token. If you notice, the don't got separated into two tokens, do and the negation here, NT. The question mark is also a separate token, and that is because of by default, this tokenizer here, it separates negation into two tokens so that you know what is the main word and this is just a negation of it. Some attributes that we can use for each token. So we can look at token.lima or token.isstop, and let's see what those give us, token.lima. So I'll just go to the example. I think it'll be easier to explain. So this is the same input that we have. And the lemma is basically what is the root word that our token comes from. So T comes from the word T, is comes from the verb be, healthy, and calming comes from calm. Do, NT is not, you is a pronoun, and think, that's the basic verb, and question mark is the same. And the last column, which is a stop word, is true or false based on if this is a common word. So things like a and is. So very, very common words will be stop words. For example, be or is a stop word, and is a stop word, do apparently is a stop word, negation is a stop word. So if you look at let's say a rich corpus in English, let's say a book, and if you look at the word distribution, how many times each word appears, you expect probably a or and or is to appear a lot of times. So we don't want our model to overfit or to pay a lot of attention to this high appearing words. So we have the option to, first of all, to detect them, and also we can also remove them from our corpus so that our model doesn't pay a lot of attention to these words without losing the signal from other words.
What about the comma?
Yeah, punctuation. I don't think that plays a significant role. Dot punctuation. I would remove it before I fit it to a model. David, what do you think? Punctuation, is it important?
Yeah, they don't consider it a stop word here, any of the punctuation, but that's a separate. I think that's a separate option. You can choose to remove it.
Yeah, I don't think there's a lot of signal there, right? So by signal, I mean if the meaning of the sentence of the word changes, if there's a comma there or not, or a period or not. That's what I mean.
But it could, right?
Yeah, I'm sure you can devise an example. Yeah, but in general, let's say you have a paragraph, and if you remove the commas from it, does the meaning of the paragraph remain the same, or is it flipped like significantly? I mean, yes, it will change a tiny bit, but
the opposite example is if you're building like a chat bot and it needs to ask questions back, then it better have good punctuation, right?
Mm-hmm.
So it depends on I would say it depends on your situation.
Yeah, but if we were just trying to detect sentiment, for example, yeah, I mean, I'm sure you can construct some artificial example with commas placed in the wrong places or the right places. But in general, I expect even if you ignore the commas or the periods, the punctuation, basically, the sentiment will all remain the same. Cool. Another thing we can do is, apart from looking at the basic, the lemmas and the stop words for each token, we can do some kind of pattern matching. And for that, we're going to use a library from Spacey Matcher called Phrase Matcher. So we'll use this attribute called lower, meaning we'll consider a match even if the casing is not matching. So even if my words is all uppercase or some characters uppercase, but my pattern is lowercase, it will convert both of them to lowercase word or token, and it will be able to match them. So let's look at a very basic example. Let's say I have a list of items I'm interested in searching for. Think of it as like a control F when you're doing your browser. And let's say I have a list of phone devices, so Galaxy, iPhone, Pixel. What I will do is I'll convert them to tokens, and that space it can handle. That's why we need to call this NLP text for each one of them. And I'll get back a list of now tokens called patterns. Then using the matcher, this matcher object that I defined above, you can use a name here. In this case, I'm just using the word terminology list. It could be any name. And we're adding this pattern. So telling space is basically that we are looking for whatever text we'll be dealing with, we are looking to match it against any of these keywords here, any of these words. Then if we have, let's say, 3 sentences here, and this is 3 separate sentences, and let's say each one of them is a review or some kind of mention about specific devices. So first in the first one, there's no mention of a specific device. The second one has 1. Third one has 3 devices. So when we call matcher with this input text document, we will see an output that looks a little bit like this. So the first item that we see, so it's a tuple of a few things, and the first one is what is called a match ID. That match ID is basically just an alias for this terminology list that we mentioned before. So we can have, for example, a phone a list. We can maybe have a laptop list. Maybe we can have a tablet list, something else. So in this case, this identifier just tells us that I was able to match. I was able to find a match from the terminology list here that we have. And then the second and the third result here is in our corpus, which token did we find a match for? This would be the 17th token and the 19th token. So just let's look at the very first item here. We have 1, 2, 3, 4 matches. Just look at the very first one and let's break it apart. Let's look at match IDs and the start and end. So the match ID is the terminology list. That's what we're printing here in the very beginning. And 1719, if you noticed, we're parsing or we're reading from text document from the 17th token to the 19th token, and that would be this token here. So later on, you see there's a 22nd and 23rd and 24th. So probably that's this one here. Then a 30th one, and then a 33rd one. Cool. So we basically read some text. We stored it in a format that our library can use it. We did some basic pattern matching, and that's our very, very soft introduction to just working with text. Comments, feedback, questions before we go to our first exercise of analyzing Yelp reviews. We went through that. That's the pronoun part that we saw. Great. Okay. So let's look at something more concrete then, instead of just some very basic examples. We'll be looking at an actual Italian restaurant, and you can find it on Yelp. I can share it online, but this is an actual Italian restaurant in Arizona. Yep, Scottsdale, Arizona. And you can see it some reviews. Let me zoom in a little bit. One of my favorites, some pictures. But what I want us to remember is that for each review, we have the text. We have, sorry, how many stars did it get? 5 stars. That's important. That's the rating. There's some other features here like useful, funny, cool. We're not going to use them. You could use them if you want. But each review, the most important thing that we care for is how many stars did it get, what's the rating, and how is that correlated with the text here. You know, as you can see, it could be a few sentences or it could be a whole paragraph. here. Awesome.
Are some of those pictures or text?
Many of them are just text. Some of them have images, but we won't be working with images for this exercise. We'll just be working with the text and the rating for each review. So let's look at the data and see how it looks like. So we'll be importing pandas, and these are some libraries that Kaggle courses use just to check your code to make sure that it works fine. So I'm gonna make sure this is turned on. Okay, I didn't turn it on. There you go, let's go back. And our data here is stored in this JSON file, and let's read it using pandas read JSON method, and let's look at the structure. So we have a review ID, which is the ID of the review. We have a user ID, a business ID, in this case, a restaurant, and you can see it's the same. How many stars did it get? How many stars did this user give for this review? 4, 4, 5, 1. So you can get from 1 to 5 stars, basically. There's some other features that we saw, like useful, funny, cool. We won't be using them for this exercise. Then the actual text. So I used to work for a food service and this and that. And we can look at the full text for any review if we want, and the date. So to really work, the challenge that we have is, so this is the data. What we'd like to do is, the business owner suggested that we use reviews from Yelp website to determine which dishes people liked the most and which one people liked the least. So we want to basically score our reviews or our dishes based on reviews. So we have the data here. Not only that, but as you can see here, we have the reviews, but we don't really know here from the text which dishes people commented about, right? So we have to read the text. We have to figure out, is this about a salad, a pizza, some kind of a pasta? You know, there's so many other items that the restaurant has on their menu. So to help things out for us, the restaurant owner gave us a list of all the items in their menu. As you can see, this is all the items they have on their menu. Eggplant, tiramisu, chicken pesto, grilled vegetables. Let's say this is pretty much the list of items they have on their menu. So now we have reviews, we have pure text, we have reviews, we have our ratings, we have what items we have in our menu. What we want is for each item, it would be nice to have some kind of average score across all reviews. So for example, you know, cheesesteak, what is the average reviews on our data set? Or maybe grilled vegetables, how popular is it? Did it get on average 2 stars, 5 stars, 4 stars, and so forth? Cool. So as you can think, we have words in the menu that we need basically to search for in our reviews. So this looks very similar to the phrase matcher exercise that we did before. So for that, first of all, we're going to import Spacey, and from matcher, we're going to import this phrase matcher. We will look at only one specific location of our reviews, and that is just the 14th review, just for testing purposes. And this is the review. El barista sandwich has become a staple in my life. Some ingredients here. So this is the text. This is in English. We'll be importing what is called a blank model in English. Taking a look at that. And we'll be tokenizing it. So basically we'll be storing this in a format that our library can work with. It didn't really change much. If you notice, I didn't see significant change. So then the next thing we'll be doing is creating this matcher object using this lower attribute to match words regardless of their uppercase or lowercase. Then for each item in our menu, we have, I don't know, let's say 30 items in our menu. We'll be creating them, we'll be tokenizing them or storing them as tokens in our list. So I didn't run the menu. There you go.
So one thing about that lack of change there on the blank model, I think that's the difference between loading the blank model versus the, I can't remember which one we loaded, what the name of the one was in the exercise, but it actually had some representations in it, so that a word like my, it captured the word you, the pronoun. What was it? It's basically .load, that's what it is, versus blank.
Mm-hmm. Yeah, this one, the English one, has a lot of attributes and methods and what are called pipelines in the backend. In this case, we're just creating one from scratch.
But that's why it doesn't convert like the word my in that first sentence to the pronoun, possessive pronoun.
Got it. Okay, yes, that's a good observation. So we have our match. Let's look at the last 5 items on our list as tokens. To actually add them on our match list, we have to call this method add. We'll be giving it a menu. In the tutorial, we gave it a menu of terminology list. In this case, we're just going to give it a name of menu. And we'll be giving this token list that we created above. And that's a phrase matcher object. And now we'll call this matcher object on the entire document to see how many matches we got. And review doc is a very small subset, if you remember. It's just one example. So just in that one review, we're able to find 3 menu items. And let's look at the first one. This looks like it's an item from the menu. Prosciutto is another one. Meatball is another one. So basically, we're able to search in one review and find menu items. Cool. Yeah, I think this is just another one. Now we actually want to search for menu items in the whole data set. Not only that, but we also want to grab the ratings for each item in a list and do some kind of pre-processing after that. So for that, we'll use this default dictionary, which is a nice way of basically working with dictionary of lists. We'll be creating a blank one here. Let's check it out and see how it looks. It's empty right now. Then the next thing we'll be doing is we'll be iterating over each of our data. So let's look how much data we have, and let's see what the structure was again. So we have about 1,300 reviews. And let's look at a few of them. So we'll be interested in the text as well as stars field here, the reviews. So we'll be iterating over each of these 1,300 reviews. We'll be converting the text field into tokens, storing that into this document. I have a debug option here if I really want to look at each individual step. For now, I just have it to false. Then I will match. Remember, our matcher has the menu items for each review. I'll match. We'll try to find menu items. We'll store that in the matches. We'll do a little bit of processing here. We'll basically convert everything to lowercase because somebody could have spelled a menu item with uppercase or the first character with uppercase. So what we're doing here is we are basically finding each item from each review and storing that in lowercase. And then from there, we'll be using the menu item as a key in a dictionary right here in this item ratings dictionary. And from there, we'll be appending in a list the reviews. So this will make more sense once we look at the structure of this item ratings. And so we have 43 items that we're able to find. And the structure is we have a menu item and it's in lowercase, and then we have a list of ratings. So the more ratings or the more reviews an item have, the longer this list will be. The less ratings or reviews it had, the less items you'll see here. So for example, eggplant, let's see, had, actually, let's look at all of them. Had a lot. I'm just looking at maybe the last 5 reviews here. So 4, a 3, a 1, a 5, and a 4. There's a lot of opinions basically here. Great, now we want to sort them, or maybe we want to calculate the average review. So one way to do that is using this dictionary construction here. So we'll be using the item as the key, and we'll be using, so actually the way to read this is from the second part. So for each item and rating in our dictionary, we'll be looking at the sum of all the ratings divided by how many ratings it had. And we'll create a new dictionary of item as the key and this average score as the value. So dictionary comprehension, that's the word I was looking for. So now remember, item is our key, and you'll see now just a number instead of a long list of reviews. And you see some items are popular on average, 4 point something. Some of them are not that popular. Some of them seem popular. And the next question is it something that we can fully trust? Basically this average score here. So for example, artichoke salad got a average review of 5 stars. Do you see any drawbacks or any weaknesses with this approach of trying to pick which items are the most popular or the least popular here?
So if you only have one review for artichoke, and it was a 5, it's just going to show up as 5. Might have been the only person ordered it.
Got it. Yep. Exactly. Yeah. So basically, don't know how many people reviewed that item. So we can find maybe the worst, or the worst. I mean the least popular item, or the best popular item. But what we actually want is we want to see as well how many people actually rated an item. So to do that, we'll create another dictionary with item and how many ratings each item had. And let's take a look at that. So this one is now a different picture. So regardless of the rating, pizza was the most rated item. It's an Italian restaurant, right? Pasta, meatball, cannoli. And let's look at our artichoke salad. Yep, there's only 5 reviews. Maybe all of them are 5 stars, but apparently it's popular there. It's very good from among the people that rated it. Now what we want to do is we want to show the worst as well as the best rated items, as well as a count of how many people rated it. So for example, the corned beef here had an average rating of 5, but only 2 people rated it, or the next one, turkey, 1. So basically, maybe we wouldn't trust anything that's very low in terms of reviews. But for example, this one had 50 reviews and all of them said, you know, pretty decent, pretty good. And then in terms of the lowest one, I mean, 4.1 is not that low. The chicken cutlet was the least popular one on the item, if you remember, and 10 people reviewed it. Great, so then we can take this information, we can take it back to the restaurant owner or the manager there, and we can say that, you know, this is your average rating and how many people rated it, and maybe there's something you can do for these items, and maybe you can advertise better these items, or maybe you can improve a little bit how you make these other items. Or maybe you can call Mr. Gordon Ramsay and have another episode of him showing up in your restaurant and trying to make things better. Yeah, and that goes back to the question of the less data you have, the less trust you can have in your average rating. The more data or the more reviews you have, the more trust you can have in your scores. Cool.
Can I ask a quick question? Is it if one review has mentions multiple food items, I assume, and only has one review score, I assume all those food items are getting the same score assigned to them? In this case?
Yeah, that's a good one. Yes.
Because some might have had a more complex, I like this, but I did not like that, or something, and that would get missed. In this case, it's a limitation.
Yep.
So if you want your review to count really strongly in these averages, just list a whole lot of foods in your review.
That's a way of, are you trying to tilt the balance here? With yeah, that's a good approach, right? If you list a lot of items and give 5 stars, then each of those items will basically get 1 count and a 5-star review. Okay.
So maybe a more advanced approach might look at the number of food items and not assign quite as much weight to a review that mentioned 20 different food items.
Maybe you dilute your rating the more items you have, maybe. So the more items are mentioned in a list on a review, the less, the more the rating is diluted among them.
Or you could see if the same reviewer is making multiple reviews.
Yep.
Could you add weights then? Is that in NLP, like, can you add weights to, I guess in this case, depending upon how many items were mentioned in a review?
Mm-hmm. Yeah, I mean, you could do it. You could do it even outside of the NLP library, because you know how many food items are mentioned in each review. You know the rating for that review. So you can construct your own weighting system, I'd say.
Yeah, for each of these reviews, we got a list of matches back, so you could just count those. Just an alternate approach. I don't know how much extra value that might add given the simplicity of the problem.
Mm-hmm.
Also, a lot of people will mention a lot of the food that they had, but the review is really not going towards the food, but to the general experience at the restaurant. They might say, I really like this restaurant, and that's why I'm giving it 5 stars. And the reason I like this because I like this, and that.
Yep.
So it doesn't really mean that any particular menu item scored those stars, but that the overall experience scored those stars.
Yes, you got it. And we'll look at a richer data set so this is only for one restaurant. We'll look at a richer data set from Yelp that has other type of businesses as well. So it could be coffee shop, it could be maybe business. And yeah, you're right. It's not just a specific item. Maybe it's the atmosphere, the personnel, the staff, how clean it is, what's the parking situation.
And just to be clear, I just pointing out, I mean, it's maybe obvious to people, but we're not doing any machine learning, deep learning here. This is, data analysis, basically.
Yes.
Showing the power of getting the data into a format with Spacey where we could do this analysis quickly.
Exactly. So basically, we're trying to pattern match words here and assign them some kind of a value, which is the rating here. So in this case, if you just ordered eggplant and the salad, we'll assign it 5. But if you ordered a lot more things, then all of them are going to get the same ratings here.
Maybe you could look also the variance on the rating.
Mm-hmm. Yeah. And these are just some other documentation. I was looking at the add method, the lower, how to convert everything to lowercase, because some items were uppercase or lowercase. Some other resources I found online. Cool. I want to make sure I give a lot of time to David. So we'll be jumping on the second module here, which is doing text classification using Spacey again. So for that, we'll switch gears a little bit. We use a slightly different data set, and let's look at the structure of it. So we'll be using this spam.csv data set. We'll look at just 10 records of it. And we have a label and a text column. And the label could be ham or spam. Ham is valid text or email. Spam is you don't want to open it and waste your time there. And somebody labeled them. And you can see the label and the text. There are many approaches you can do here to classify your text or your document to one of these two categories. The simplest approach you'll be using is what is called a bag of words. And how that works is you look at your entire training corpus. So let's say my entire training corpus for this very specific reason is, let me zoom in a little bit more. T is life, T is love, somebody really likes T here. T is healthy, calming, and delicious. Let's say this is the entire data that we have seen so far. Then the vocabulary for this would be T is life, this is repeated again, love, healthy, calming, and delicious. So ignoring punctuations. Then the way that we would encode this first sentence here is, this is our vocabulary here. We would count how many times or how many items from our vocabulary each word appears. For example, in the word T is life, T is love, the word T, which is the first item in our vocabulary, appears twice. That's why there's a number 2 here. Now the next one is. There's an is here, there's an is here, and that's our second word in our vocabulary, so that's why you see a number 2 here. Life is our third word in our vocabulary, and it only appears once here. And love is our fourth item, it only appears once here. Healthy does not appear in this first document, and so for the rest, calming and delicious. That's why you see zeros here. Similarly, for the second sentence, T is healthy, calming, and delicious. T appears once, is appears once, life appears 0 times, love appears 0 times, healthy is once, calming and delicious appear once. So basically we went from text to a vector, and that's the main challenge for our main pre-processing challenge we have to face before we fit it to any model. We need to convert text to some kind of a vector. So this is what is called this bag of words, because if you really think about it, it's just a collection of words or aliases for words. So there's a note here that documents with similar terms will have similar vectors. So let's say maybe our vocabulary had thousands of unique words. Then documents, let's say that are talking about tea or coffee or healthy, this and that, you'd imagine that their components, if you try to visualize them, not visualize them, but somehow maybe represent them in a higher dimensional space, that they would be somehow close to each other. But as you'll see, this methodology is not the best way to represent data and doesn't have a lot of nice properties compared to other approaches. Another one is this term frequency, inverse document frequency, where you look at how many times a word appears and scaling it according to that term's frequency. So for example, if I have a sentence that the word T is mentioned 10 times, maybe I shouldn't mention it. Maybe I shouldn't give a higher value in that index of the vector. Maybe I should scale it by how many times it appears so that it's a little bit more normalized. We're not going to work with this TF-IDF approach. We're going to just work with a bag of words model here. And to do that, we'll work with this text categorizer class. So as you can imagine, this is a classifier basically using text in Spicy. To do that, we'll use this larger Spacy model called the English Core one. And I think that has some way more attributes and way more features than the blank one. But for simplicity, I think we're just going to go with the blank one for now, the English one. We'll create this pipe, which is basically our text categorizers. And the way we do that, we give it a name, textcat. That's the alias for this text categorizer. And 2 attributes, the exclusive class is true, meaning that when we classify a sentence or a document, it can either be one or the other, it cannot be both. And the other one is called an architecture, which is BOW, which is bag of words. If you look at documentation, sorry, I'm trying to find it here. If you look at the documentation, there's some other options for you as well. You can do the simple CNN, which is based on convolutional neural networks, or you can do what is called an ensemble, which combines both bag of words and the neural network as well. For now, we're just going to use this bag of words model. Cool. So we define this categorizer. We'll add it as a processing step, or as a pipeline here in our NLP method. And there's a description that I was mentioning about the attributes. The next important thing is we need to add our labels. In this case, we have two labels, ham and spam. So we add them by calling the add label method. Now we need to train our model of for each document, this is a ham or this is a spam based on our training set. So we'll be looking at the text field for each of our reviews, or for each of our documents. We'll look at the values part of it, and then we'll create this specific structure here. So we need another dictionary called categories here, cats. And then within that, we specifically need both the classes to be present. So it's not just that the label is either there or not there, so true or false. So ham, for example, is true or false. We need ham to be true if this is ham, and spam to be false, and the other way around if this is spam. So we're going to look at it a little bit of it, how this looks like. So this is the text, one example. And this is our label data. We have a cats. All of them have this cats categories key. Then the ham is true, spam is false. So this is basically a valid review of valid text. For the other one, ham is true, spam is false. And the last one, this clearly looks like spam, so ham is false and spam is true. This is just the structure that this text categorizer in Spacey expects. The next thing we'll do is you can fix this random seed in your model. That's just for reproducibility. The other thing is in the backend, Spacey needs to allocate some resources for you to begin what is called training, and also give you an optimizer of how would you proceed from step to step while you're training your model. Then we have, let's say, thousands of reviews or thousands of entries. We're going to look at 8 of them at a time using this mini batch library over our training data. And for each batch in our batches, we will get the text and the labels, and we will train our model. And the way we do that is by calling this nlp.update using the text and the labels and using this optimizer. And if you notice this loop, this reminds us a lot about classical deep learning approach, where we had, in this case, one epoch. We went through all our training data in multiple batches. We had a fit method, and where we had our train and y or labels. We had an optimizer, we had a loss function, we had some metrics as well. In this case, we're just looking at optimizer. So this is one training loop or one epoch through the data. To really make this work, we need to have another outer loop, go over our training data 10 times basically, and do the same thing as we did before. And we can also print a loss here. And for this example, for some reason, the loss keeps going up. I would expect it to be going down, but in the exercise, it went the other way around. It started high and then went low. I'm not sure why in this specific example it started low and went high. That's not something you want to see. So let's say after 10 epochs, we want to make some predictions. So we have a text here, or in this case, 2 examples. And we want to ask our model, you tell us if this is ham or spam. So we need to tokenize them. Then we need to get our model output ready. And then we need to call this predict method on our text categorizer using this document. And you'll see scores, and the scores will be in the form of a list because our labels are also packed together. So this is the score for the first label, ham. This is the score for the second label, spam, for this very first sentence. So looks like this is ham, right? 0.9. And for the other one, it's like it's the other way around. This is spam. You can also pick the maximum number for each one of them and pick the maximum index. And using that maximum index, you can assign it to our labels, and you can get basically the actual output in human readable format, ham or spam. So all that is saying is that in our original text here, the first example is valid ham, and the second one is spam. That's it. I'll quickly go over the exercise. I think it has a richer data set. I won't run it this time. It takes a little bit of time to run. So to give you an idea, this data set now is looking for, and I got a little bit thrown off here, but we're looking at reviews, but the reviews are not coming from people on the app or online from Yelp. They're actually emailing the owner the reviews. Let's say that's a feature that this restaurant supports. So the restaurant menu includes an email address where visitors can give, let's say, anonymous feedback or private feedback about their food. You don't want people to look at a review, so you directly contact the restaurant owner about your review. So this is different than the data set, or not different, but this is slightly different than the data set we saw from the Yelp reviews. What are some issues that you could see with training a model on our Yelp reviews and then trying to predict? So let's say we train a model on Yelp reviews if the review is positive or negative, and then we're trying to predict the sentiment or the overall sentiment of an email. And what can go wrong there? Think about when you write a review on Yelp versus when you write an email. Do you use the same words maybe? Do you use the same sentences? Do you use the same language per se?
There's also going to be selection bias. Different people will write emails.
Right? Yeah, they'll have like probably a greeting at the beginning, maybe some introduction, maybe the main topic, and then maybe a conclusion, right? It has a structure to it. Yep.
Also, in terms of context, I mean, now people are writing directly to the restaurant owner or management, and it's not a review meant for the world. So, it's going to be structured differently just because of that.
Mm-hmm. Yeah, exactly. So the good thing about this approach is that we can basically we can use our model. If we train it on Yelp reviews, we can use it on emails, but the weakness is that the way the reviews are written on Yelp might be different than the way we write emails, right? So we maybe use specific words or slangs in emails. Maybe our model has never seen them in our Yelp reviews, so maybe our prediction won't be that accurate on emails. Another approach that they're saying here is that if your model basically cannot detect if a review is coming from email or Yelp, then that's a very good model. But in this case, they're saying we don't want to evaluate that metric. But they're saying if you really want to build this, then you really have to evaluate if your model cannot detect if a review is coming from email or Yelp review, then by all means go and use this model. But if there's clearly distinction there that the model works really well on Yelp reviews but not on emails, maybe you need to retrain it on emails. Cool, so let's quickly browse through this. We have our Yelp ratings, and I think these are not just restaurants. So I looked at the Yelp website here, and you can see the category list has education, financial services, food, pets, restaurants, shopping. So it's really diverse. So we have a text, a star, and a sentiment. The sentiment is 1 for positive, 0 for negative, and the way it is if it has 4 or 5 stars, then the sentiment is 1. If it has 1 or 2 stars, then the sentiment is 0. Anything between, I think it's dropped from this data set. So the sentiment can either be 1 or 0, basically. So we did this data set here. We're gonna save. We're gonna shuffle it. In this case, all of it, 100% fraction 1. That's what it means. we will create this positive and negative dictionary. Then we'll split it on a 90-10% ratio. So 90% will be our training set and 10% will be our test set. And let's look at it, how it looks like. So let's say we look at the first few training examples. That's the first one, some of the best sushi I've had. Positive is true, negative is false. One of the best burgers I've had. Positive is true, negative is false. That's how our training data looks like. Then we'll use another model from Spacey, blank in this case. We'll create our pipeline using this text categorizer, TextCat. Similar to the tutorial, these are exclusive classes. A review can only belong to positive or negative sentiment and a bag of words architecture. We'll add it to our model. We'll add our labels, negative and positive. I try adding the other way around, and Kaggle expects this in this specific format. I don't think it'll make a difference, but that's interesting in that they were expecting the specific order of labels. I didn't see anything in the data that would tell me to go in that specific order. Cool. Then using it mini batches, we'll shuffle our data again, our training data. We'll use 8 reviews at a time, and for each one of them, we'll update our model using the an optimizer that we're expecting as an input here in our train method. We'll also be logging our losses so we can print them later on and see how they look like. So there's some pre-processing we have to do. We have to define our optimizer. We have to zip together our training text and train labels in our train data. And then we have to call our custom method that we define above with that optimizer. And then at the end of the day, just print the very last loss. Then we can try this on. We can do I'm not sure what method this is using, but this text is tokenizing it. I don't think it's using our model, so I'm not sure. Did you get this, David or Robert? I'm not sure this doc.categories, how I was able to figure out these probabilities based on negative or positive. So it's not using our predict method that we're going to use right now. So in this predict method here.
Well, that NLP up there, I thought was the predictive model. The right in that block NLP function in the second line there.
That's right. I believe that's true.
This one here? They just named the model NLP.
Yeah, the model is NLP, but to actually do prediction, I thought you had to actually specifically call predict on your text categorizer. So maybe it's using its default, maybe it has a default model built in. I was actually looking at the code in the backend later on to see what's going on. I was curious, yeah. Or maybe it's a shortcut for calling predict. I don't know. They didn't dwell in it, so maybe it's a shortcut for actually calling the predict. So in this case, we have a custom predict method we're defining. We're creating a tokenizer for each of our words. We're getting this text categorizer that we define above. And here specifically, we're calling the predict method on each document. We're picking out the maximum index of each label, and we're printing out the predicted class. So for example, let's say we have 4 reviews that we want to analyze as sentiment as positive or negative. 1, 2, 3, and 4. See, the length could be anything. So the first 3 are positive, and the last one is negative. And let's see why. So it looks like looks like a vet place, and somebody had an issue with their dog, and they're saying that the office didn't accept new patients, and you needed to book an appointment 6 weeks in advance. So the sentiment is negative basically, versus the other 2. This restaurant is fantastic, or the other 3. I will definitely be back for more. Both were tasty, so 3 positive sentiment and 1 negative sentiment. So it looks like on those examples it was doing good. Yeah, that's the same one. So we just look manually at 3 examples, but what if you want to look at more data and how do we evaluate if our model is doing a great job? So to do that, we'll create this method called evaluate, which will take our model, we'll take text samples and labels, and basically it should tell us, we know basically the true labels, we know our predicted labels, it should tell us how many of them did we get right. And so we call our model using predict, the custom predict method. The true class is based on the labels that we have from our data. We want to count how many times our predicted class is equal to the true class, and we want to average basically how many times that happens, which will give us an idea of how accurate our model is. So let's go here. So we'll look at our model, we evaluate it on the validation text and validation labels. These are data that the model hasn't seen before, so it's not overfitting or any leakage or anything like that. So we get about 94% accuracy on categorizing sentiment based on text we haven't seen, which looks pretty good. And if we do this, I think we did it before for 1 epoch, or maybe, yeah, 1 epoch. If we do this, train evaluate for multiple epochs, then we see here the loss, which is decreasing, and the accuracy, which is about the same, 94, 94, 94, 94. Yeah. So accuracy is not improving, but loss is decreasing there. So we have a pretty accurate model, even with just 5 epochs here. Cool. That's for this classification task. I'd like to hand it over to David if there's no more questions, but yeah, very, very basic, very simple. If you come from a TensorFlow Keras background, then some of this terminology looks very familiar and it's kind of natural to follow, I'd say. Let me enable it. Perfect.
All right, so the third part of this course has to do with a more sophisticated way of modeling text and relationships between words and text. And that's called word vectors or word embeddings. So they introduced how to do that with Spacey. Word vectors are basically a vector of numbers that represent the words and give you meaning around that word. So instead of just a single number, which we were using before essentially, or a count of the number of times that word is in a text, we're going to actually have a full vector to represent that number. And often these vectors can be hundreds of values, hundreds of numbers, even larger in some cases. But in our case, some of the ones we're going to use here in the examples are going to be 300 numbers to represent each word. So this is embedding. It's a very crucial step for most machine learning models, whether you're looking at deep learning or other types of machine learning. Here, I wanted to take a look at these diagrams where they're showing a couple of words, and they're trying to represent these vectors. Say we only had 3 actual numbers in there and represent them visually. But oftentimes this space would be much more than just X, Y, Z. We would have, as I said, like a 300 dimensional space that these vectors live in. But as we know, words can be very similar and have common meaning. For example, here they've got the idea that walk and walking in terms of verb tense in the middle are very similar in terms of, if you look at swimming and swam and you drew a line between the the words, you would see they would point in the same direction, meaning they have the same kind of relationship to them because these are the same, these are different verb tenses of the same word. They do the same thing with countries and capitals over here on a larger scale. They do something here with man is the woman as king is the queen. This brings up an issue that you see in terms of bias in data and machine learning, where if you were to look at the line between man and king and woman and queen, that's very similar. But what if this was like, instead of king and queen, it was doctor and nurse? The line from man to doctor might be in the same direction as woman to nurse, but you wouldn't see a direction woman to doctor might be different, which would indicate you've got bias in your model and they should be pointing the same way. That's a whole nother subject that we can get into some other time. But anyway, that's kind of what vectors are in terms of embedding for words. And we can do this with Spacey. We're going to start off by loading up our large model. This is the core web large model. I did a little bit of investigation around it. It's, I believe, here. It's got 685 keys and unique vectors around them. There's each of these vectors or these embeddings, each word in here is embedded with a 300-dimensional vector. The actual training of these embeddings, in other words, how did they figure out how the words relate to each other to come up with these numbers for these vectors? They used a very popular source called Glove, and that's the actual pre-trained embedding, and it was trained on something called a common crawl. I won't go into Glove too much. The common crawl is basically, you've heard of web crawling. It's where they've looked at millions and millions upon of web pages and the text that's on those pages to come up with these relationships between the words and teach the models. And in this case, it's an English version. The Common Crawl has over 40 languages, and this is the English version. So back to our exercise. We're using that version of trained word embeddings in our model. And we're only going to look initially just at how it handles this text. So here's a small source of text. We're going to use our NLP model that we have, which is going to create embeddings for us around this text. Out of that, we're going to token those, and we're going to get vectors, right? So each token now, instead of being a single number, is now has a vector component to it. These vectors, as we said, we've got 12 words here, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 12th is, I think, is the period. So it's concluding that. And so each of those 12 words have a vector associated with that's 300 dimensions. One vector for each word, as they say, and that's our embedding. So we're going to see how we can use those, and we're going to go back to the spam or ham type of data set that we were looking at before for those messages. And we're going to get, instead of getting just the word vector, we're going to get a document vector. So before, we were getting a vector for each word in this text, right? But what instead we can do is get a representation of this whole text as one embedding, as one document, what they call a document embedding. And that can be done several ways. In this case, we're going to average all the word vectors across that document to get the values. And I'll go through this a little bit more in the exercise. So I'll go through it a little more detail there, how it's done. But that's what's going on here. We're pulling in the full text, not just the token, the full text, feeding that into our NLP, which gives us our document back. and then the document has a vector associated with it. So just like we were looking at token.vector, we can use document.vectors. And we're going to put those into a series of vectors here. So this array of document vectors, we've got 552 emails that we're deciding whether they're spam or non-spam. Each document vector, again, has 300 dimension embedding associated with it. For this, we're going to try to classify binary classification of whether they're spam or ham. We're going to take our set of document vectors. We can feed those into our chain trust split, and we're going to save 10% for testing. Each of these spams came with a label, a 0 or a 1, for whether it was spam or ham, as George showed earlier. So that's going to produce our test sets and our training sets. Our first model we're going to use comes from sklearn. It's the support vector machine model, SVM. We're going to use the linear version of that. It's a very straightforward model. I won't go into too much detail about how it works, but basically we're going to initialize that and do fitting or training on our data. We're going to then evaluate it on our test data with this helper method here called scoring. This is an accuracy scoring it's a simple accuracy scoring. Did you get it right or wrong? And then that's averaged across the whole data set. So that comes out very well for SVC on this. It's 97% accuracy. This is very, very good. The next concept I'm going to look at is called document similarity. There's many times you may want to look at certain, even something like spam, and you might want to look and see if there's a similarity between the way authors of spam are writing their messages. Often it's coming from the same source. It can have very similar text in it, the same kind of spelling mistakes, the same formatting. So a lot of similarity can be done for analysis. But the first thing we're going to look at for document similarity is something called cosine similarity. It's used for many different types of comparisons. You'll see this used for even for images and any other kind of data you can do that's expressed in terms of vectors. So if you recall, cosines are here, this depending on this angle between these lines, it's adjacent and hypotenuse. It's the adjacent over the hypotenuse. When they are parallel to each other, in other words, if they're on top of each other, this angle is 0, the cosine of 0. The hypotenuse and adjacent are the same, so they're going to be equal to 1. So the cosine of 0 is equal to 1. And that means that these lines are very similar, right? So if you're looking at cosine similarity, the higher the value when the cosine goes to 1, that means whatever your vectors you're looking at are very similar. If they were pointed the opposite direction, 90 degrees opposite of each other, then the adjacent would have basically synced down to 0, and it would be 0 over infinity for hypotenuse. So you would have this equal to 1. So I'm sorry, you would have this equal to 0. So the cosine goes between 0 and 1, and when you look at cosine similarity, you're looking at values between 0 and 1 for that calculation. So I'll go back to here's another way to do that calculation. It's just the dot product of your two vectors, and then you divide that by the magnitude of each vector. Similarity, actually, I kind of said it wrong. If they're pointed exactly opposite of each other, it can go to -1. So you have vectors that have no similarity at all. And here's the formula in Python for it. And we're going to just add an example. Reply now for free T. Here's some words in the second one. Document here, the vector for this that has T in it, and I don't see anything about free or anything, but there's enough similarity that we got a pretty high rating here. So these two documents are considered to be fairly similar to each other. Any questions on that?
Interesting.
Okay. So let's go and look at the exercise. I think I can show a lot more in that. All right, so As mentioned before, we're going to use embeddings. We're going to load up all the libraries that we need and some of the Kaggle tools. So the first thing we're going to do is load up this very large model of language, English language. And we're going to look again at the Yelp ratings that George looked at earlier. And you can imagine these have text and stars. And we're going to give a sentiment of 0 if it's I think between a 1 and a 2, and 4 and 5s or 1. So we're going to try to predict sentiment based on this text. So we've got a binary calculation. We have over 44,000 reviews here, which is a lot for us to work with. Printed out a few things here just to take a look at these. So I mentioned some of this that I would go into more detail. So here I'm just going to get the first one and get the text from the first one. And this is the document that results. It is done very little really to change the original text. I think I would have to go and check and look at it really closely. But we don't see any of that pronouns, or it hasn't stripped any of the, it hasn't lowercase, it hasn't stripped any of the punctuation or anything. So that's our document. And now if we want to look at the vectors around those, we can print those out. And as you recall, it's going to be 300 dimensions. So we're going to have 300 numbers that have already been trained on these words in this document to learn an embedding. So here's the embedding for that document, for that review. And those are the kind of input to our model that we're going to be using. Again, I just printed out the size of this to verify that we have 300 dimensions in our embedding. Okay, so the first thing we're going to do is we're going to limit ourselves to only 100 of those reviews, because it's going to take a really long time for us to do this next step if we do the full data set. So the first thing we want to do is get our document vectors for each review in the table. So we're going to go through here. You can read the list comprehension here is that for every review in the rows in the review, we're going to feed that into here and get the text from it. This NLP is going to give us a document, and we're going to get the vector for that document, and we're going to have it as an array that's going to go into our shaper vectors. So as I recall, we looked at 100 of them, and each of them should have a vector associated that's 300. So our shape of our vectors is 100 by 300. And then they do a couple things where they ask you about it. Behind the scenes, they've gone ahead and done a calculation of these vectors for the whole data set, not just the first 100 rows. And so they've pre-calculated that for us, and we're gonna load that in here directly. So this is interesting that, you know, you can put it right in like that. And apparently there's a nice way to save, since they're just basically numpy arrays. You can pull it in. So we have our input now. We've got our vectors for the documents, and we're going to try to train them just like we did in the course work earlier on the previous tutorial. We're going to use this linear SVC. First thing we have to do is create our test and training set. We'll do that again, same sizes, 90% for training and 10% for testing. And we're going to fit this, and we're going to print out the accuracy. In this case, the accuracy is about 93, almost 94%. So very good accuracy on sentiment for these Yelp reviews. Okay. So I was wondering, they had another thing here where you could add in a different model as an option. You could add another model, a different kind of model from instead of support vectors. And I was wondering just how much imbalance we have. We have you know, positive and negative reviews. Well, what does that look like? So I printed out those. It turns out in this is for the full data set. Most of them are, I have to print the ones, but I think there's a pretty good mix in here of, sorry, not a good mix. There was a pretty big imbalance here. So almost, you know, 3 to 1. So I thought maybe that would be important to increase our accuracy, but maybe not. So I wanted to look at a random forest classifier, excuse me, which is another way of, it's a tree-based model for looking at data, works very well with this. So I'm going to build that with these values for parameters. I'm going to do a fit just like we did before and print out the accuracy, but I'm not taking any impact into account for this imbalance. So I'm going to see how it does without dealing with that. I'll print that out. I'm going to do a classification report, which will tell me a little bit about how well it did on the zeros and the ones. And then I said I'll run it again with class weight balance, which tells it to now balance the accuracy or its attempts to do better on the minority class. So those zeros, let's see if we can get a better result. Again, I'll print that out. And so here's the first one running without taking into the class weight imbalance. We got 88 or 89%, which if you recall, our SVM was 94%. So we didn't do as well with our random forest. And then when I took into account the class imbalance, now we're getting, I should point out before we look at the class imbalance weighted approach. So here, F1 score is the thing I'm going to look at, just how well it did on both. You can see it did, the minority class was the zeros. It did a little worse on those, right, which is to be expected, 93 and 75. So let's remember those numbers. So when I did it with balance weighting, I got an 87, which actually was went down. So attempting to do better on the zeros didn't help our model overall, but that's not surprising. But did it help much here? Well, it turns out it did not. It's basically the same. So 75.93 and 68.92. So we actually did worse on both, which was a little bit surprising to me.
Well, I guess that kind of makes a little bit of sense because the metric that we're looking at here is accuracy, though. So if you want to optimize overall accuracy, it makes sense to train the model on a data set with the same balance that you're going to be testing it on.
Yeah, that's true. That is 100% true.
So I think if you're trying to improve performance on the minority class, a technique like you used is absolutely essential. But maybe the metric doesn't necessarily reflect that.
It could be, yeah. I could have printed out like confusion matrix and some of those things to see what's going on. But it was interesting that I couldn't get the as good a result as the SVM model did, right?
And FYI, the first time we used SVM in our journey.
Or
so
SVT,
far, so, yeah.
Yeah.
It is surprising. I would have thought that a random forest could have done a little better.
Yeah, I didn't do a lot of tweaking with the hyperparameters, so probably there's some magic here I could have done to I could have done a grid search and got a much better result.
Do you know when you do that class weight equals balance, what kind of balancing method are you using? Are you oversampling the unrepresented class or undersampling the overweight class or something else?
So my understanding is very similar to, it's not oversampling or undersampling. It's penalizing the it's very similar to like how you penalize loss functions based on, right? So it puts more emphasis on the minority class. You know,
so a miss on minority class has a higher loss than a miss on a majority class.
Yeah.
Oh, so it's not doing stratified sampling?
That's a good question. Yeah, does it do stratified sampling in each tree for the samples it sends each tree? I mean, yeah, right, to each leaf, right?
Yeah, the documentation in sklearn does make this all clear. I just can't remember what's
I can't remember off the top of my head, yeah.
Okay, I'm gonna look it up.
But it is a good place to look. They do describe it pretty well.
Yep.
Don't you think they would have, Kaggle would have figured out the model that worked best for this teaching exposition? So
it's possible they would have used something that was good enough and fast.
yeah.
So that's another criteria is speed. for
Mhm.
something like this. Yeah. We probably could fool around with random forest parameters and get a better model, but it'd be very slow.
Mm.
A very large model. Yeah. Anyway, just something I thought it was interesting to take a quick look at. All right. And so the second part is remembering that we were talking about document similarity. The key for that is we're going to just look at the vectors here and see what we can figure out. One thing they talked about is that sometimes people center the documents. It's very much similar to normalization that we've seen before. They're going to look at the mean vector for all the documents and subtract out each individual document's vector. Let me see if they have an example of it. Yeah, so I had to code this, of course, but here's where we're looking at all the vectors from our document, right? And this is what they gave us. We read it in a long time ago for all the vectors for all the document vectors for all the reviews, right? So they go through and they calculate the mean for all those document vectors, and they're going to subtract that from the vectors that we're going to compare to, as well as this particular review here where they produced the vector for it. And we're going to be centering around our collection of reviews and do our cosine similarity for these centered vectors. And I'll go through that in just a second. But so they do that for both the total number of vectors and right in here, we're going to do it for our particular vector, right? So right here, we're going to subtract out the mean for this one too. And then we're going to apply our cosine similarity. So for each vector in our centered collection of rows from our data set, all our reviews, we're going to compare the centered review here to those and produce an array of similarities. So cosine similarities, these values between -1 and 1. And from those, we're going to get the maximum one. We're going to figure out which one's the maximum one. And that would represent the most similar review in our big collection of Yelp reviews to this individual example here, which is not in our Yelp reviews. Otherwise, we would get a perfect match on similarity. So that's the calculation we run. And then we print out that index for that one, that most similar, and we pull the review that's most similar. So just to go back and look at it for a second, it has to do with a tea garden. It makes mention about how the food is, slightly expensive, however, it's very good. More about the tea and a particular dish here. Very important, I think, to look here and maybe get a feel for. You might think, here's Zen, you might think there's something to do with Asia or China. It doesn't say for sure, but you get the feeling this has something to do with tea and then Asian. So I don't know, just some things I was trying to pick out. It's a positive review, that's for sure. So let's see what we got when we do a similarity comparison. So here you can see we've got another tea place. In this case, it's not necessarily a restaurant, but it's a merchant. And it talks about how it's around people that are freezing. It's by a skating rink. It's a very positive review. So we got that in common. Goji berries. I don't know, if that, it was hard for me to, I'm not sure I get an Asian feel as much from this. So maybe that's not there. Clearly, the places it's citing are not in Asia. So, but you've got definitely things about drinking and tea and very positive. And I'm not sure if other people saw some other similarities.
Yeah, I remember the review had a smell of tea everywhere. That's what I remember.
Yeah.
Smell of fresh tea everywhere. And this one had leaves of tea on the wall. So I don't know. To me, that
Right.
I found
There's
that
mention of it being in a city. I think
Yep.
there's something.
This one is in the middle of the snow, right? Somewhere in Vancouver.
Yeah, Toronto. Yeah. So maybe you can see how it picked this one out. So as a bonus, you notice they went and defined a Python function for doing the calculation. But it turns out that Spacey has this built in via the doc. So you can look at you can have a document and you can call a similarity function on it with another document, and it'll give you the actual cosine similarity. By default, it calculates the cosine similarity between the two docs. So this is kind of a shorter way of doing it. The only thing that happens here, though, is to do this, you've got to compare documents, not vectors. And if you recall, when they did the work for us behind the scenes, they gave us the vectors. So I had to go and actually produce the documents. So that's what I did here. Doc 1 is this review up here. So that's the document for this one. But yeah, I wanted to see if it would work. So I produced again. I'm getting those similarities, the array of those for each document in our collection, and I printed out the most similar. And it turns out it wasn't the same, which sort of surprised me. I'm not sure how I can explain that, but yeah, it turns out it was a much longer review. It has some similarity. It does. The reason I kind of mentioned that maybe that had the feel of Asian or Chinese restaurant or something. This talks about Hong Kong style. They do mention the tea in here, but here it says talks about being a Chinese restaurant. So I don't know if there was something there that it might have picked up.
So are you tokenizing differently? Is that, do you know what's happening differently?
Behind the scenes, yeah, that's a good question. I'm using our same NLP. It shouldn't be really.
Oh, you're right.
Yeah.
Do you happen to know if that removes stop words before doing the average?
That's a good question. Yeah.
Is that centered too?
Well, that was the thing I was going to bring up, is that it's not centered, right? If you remember, They did all the centering of the vectors, and that's my guess for why it's different. So centering really, I could be wrong. I don't have it. I need to do some kind of, I don't know how you would do this. We'd have to look at really, this doc 1 is clearly not going to be centered, right? But does it, I don't think it does. I didn't see an option for it to tell it to do centering. Because it's got to do, you're calling this on a single document, but really we're doing this for every one, right? And so your centering was based on the collection.
And that similarity is a method defined in Spacey for tokenized objects?
For documents, yes. For the tokenized text, right? But I think it is that centering that's probably affecting this. It's still not a bad match. It's just, it's interesting that it chose a different one.
Maybe it's not cosine similarity. Maybe it's some other type of similarity, like L1 or L2 or something else. Similarity.
Oh, it is doing cosine.
Oh, it is cosine. Okay.
Yeah, that's the default. That's what it goes to. So.
Is there any other approach? Like, let's say you wanted to find a similar document to your entire corpus. Do you have to literally scan the entire corpus? Is there any other way to do this? This doesn't look scalable to me, but I don't think there is another way. Like, do you have to scan? It's all vein, right?
So that's another point that I didn't do it. I did a timing on, just for example, how long did it take them to create their vectors? I think that's what I did. Let's see. Sorry, I did it somewhere. But yeah, I think I know what it was. I timed. Sorry, just remember they did this for 100, and I timed that. That was like 3 seconds, and this turned out to be like 20 something. Yeah, 23 seconds. So I was trying to figure out how long this might take me. And I figured I had calculated it to be around 24 minutes. So I figured, hey, I can wait that out. But the question you're asking is, to get all those, it would still be the same thing, because you've got to go through and create the documents, right? And then do the vectors for each here.
For docking docs, I'm saying, is there a better way instead of maybe looking at all of them? Maybe.
So I actually think the time that it costs is here. It's producing this.
Sure, but if that docs was, let's say,
This step is fast.
10 times larger, then you'd be probably spending a lot of time there. Maybe it might be a better way where you start in the middle of this 300 dimensional space and then you do radius search or something, instead of just going through each one of them separately. Like you start with a sphere and then you expand it until you find the most similar ones.
Yeah, but how would you know where they are in that sphere without?
Yeah, that's the thing, right? So maybe you have to represent them in a lower dimensional space. I'm not sure.
Sure. Yeah. And they already have done that in a way by doing document vectors instead of a whole huge thing of vectors on each word.
Yeah.
Yeah.
And the other thing I was a little bit confused here, if you scroll up, David, where it introduces the concept of centering.
Right. So their explanation of centering was not the most clear to me.
Yeah, especially the last sentence. So
yeah, let me reduce size just a little bit.
So saying sometimes your documents will be very similar. That's why you might get something in between 0.8 and 1 for similarity in one dissimilar documents. It says when the vectors are centered, you're comparing documents within your data set as opposed to
Sorry. I've lost my ability to focus here.
as opposed to all possible documents.
Right.
I don't think centering narrows your search to your data set. That's what they're claiming here.
I didn't think so either. Their explanation here was quite confusing to me.
If you center, looks a lot like correlation. Almost the same formula.
Yeah.
Correlation with what?
No, I mean the formula for correlation is pretty much the center similarity. When you look at data.
So we talk about similarity here. The centering is just removing a constant vector from your entire data set. You're just calculating it once. It's just a constant vector, and then you're removing it from all your training documents, from all your training records. So that vec mean, that's the thing. Minus vec mean, that's, what is the effect of that basically?
And if you think about an extreme case in which all of the vectors are pointing a similar direction, and then if you subtract the mean, like you're pointing, say, from the origin to this tight sphere of all your vectors, and then you subtract the mean from that, you're going to get a very different distribution of the angles. It's possible that two points on opposite sides of the sphere could have identical angles with respect to the original coordinate system.
So is centering really zooming into that hypersphere that's far away from the?
Yeah, centering is zooming in and at least forcing the objects that are going different directions from that mean to be dissimilar.
Got it.
Yeah, that makes sense. Right.
Cool. This is interesting.
I believe that was basically it. They make a point that, you might see similar things between similar coffee shops and a tea house, and, so that kind of thing.
Cool.
Any other questions?
Yes, I have clarifying questions, perhaps for both speakers. So for this last part, using the embeddings, I heard that there are 300 dimensions representing each word. But before we use each document to feed that into machine learning pipeline, I heard that it's a mean vector. Was that a mean vector or is the summation of the vector of each word that present the document?
Right. So they're taking. I'll go back over to here. So they are taking the. So here we're getting for each token, which is the word, right, within our text here, they're going to get a vector, right? And that vector is 300 dimensions. But instead of using these 12 vectors for every, these 12 300 dimensional vectors for every word in our text, we're going to do the average across these 12 words and get the 300 numbers, as you will, that are the averages of these values, so that we get a document level embedding.
I see. Thank you.
But
So
David, I was wondering the same question. Like, where is that function actually happening? Because it looks like here you're doing it on each
Right.
token, and then later on you apply the dot vector method to the whole.
Right. So
does that something that's built into this library?
it is, and I'll show you. So NLP text, right? So this is doing it on our whole text, and that's going to give us a collection of tokens, right? So it gives us a document, which is a collection of tokens, right? So what they do down here is they look for the text, which we were, if you imagine we were feeding text into NLP and getting a document that's a list of tokens. Here, we're going to take that text, we're going to feed it in NLP. This is now a list of those tokens or a document. And instead of getting the vector off the token, we're getting the vector from that whole document. And so this is a built-in method of this is a built-in property of the document. So it's an attribute that's built into the library NLP, the spacey.
So it's just a straight average, you're saying?
Yes. So it does a average of the vectors for those words. It's, here it talks about it, right? So it's simply averaging the vectors for each word in the document.
Okay. So naturally, I was wondering, like, do you know if there's other ways of combining the vectors together that are commonly used besides just the averaging?
It's a good point. I assume there may be. Do you know, George? I don't know Spacey that well. Does it have?
Yeah, I was trying to look at the code, but I didn't get the chance to look at the code for this one. The other thing to notice is, Neil and David, if you notice for text, the text here is actually a sentence, but if you're in for loop above, that was actually a token. So that's also a difference.
Yeah, that's what I was saying. Here we're going through the tokens, right? Whereas here we're doing the whole text.
Yeah. So maybe in the code they have an implementation says that if this is a single vector, then just output that vector. It's a list, then use some kind of average algorithm or possibly other ones to compress them from a 12 to 300 to a 1 by 300 matrix.
Yeah. I can imagine that there might be other, I'm just kind of guessing, but
that has to
somebody who knows a little more about natural language processing that maybe doing like multiplying them together, or do some kind of AND function or something that's not just the average.
Yeah. Or maybe popular words or stop words are removed. Maybe some kind of TF-IDF.
Yeah. Anyway, that's fine.
Because the average of the T was awesome. Who knows what's going to be
right.
like.
And I suppose that like any number will be ignored before feeding to this 300 dimension. And the other similar question is, like, if there are a lot of slang or language that is not known in the training data set for the embedding,
that's a good question. A lot of times we've seen they have a special token for like out of vocabulary. I do not know what is the deal with Spacey and Glove and those guys? How do they handle that? Do you, George, or anybody else?
I thought when you do that NLP though, it does lemmatization. So if you have like a weird word that comes from like a basic word, I think it'll just keep the basic form of the word, like the lemma.
Okay, so you do the lemmatization beforehand, before doing the embedding.
One thing that I found really interesting when I was playing with this notebook at first, just trying to learn a little bit about these objects, I executed the commands like NLP or spacey dot blank en, right? Just to see what was in a blank model.
Right.
And it turned out that if you dug down into the attributes, there was a vector of, I think there was about 500 objects. And if you looked at those objects and printed out the strings, they were all like slang and emojis.
Huh?
Just, and, you know, text emojis using characters like colons and dashes. But I couldn't figure out what it was doing with those. It's just like it had stored these text strings in the model somehow, and I don't know.
Maybe it was like an exclusion list, you mean? Is that what it was?
Could have been.
Sorry, how do I reproduce that result? Spacey dot blank.
Let me go in and I'll find my Kaggle notebook on this and post it to the chat.
Right, thank you.
What I used to get that. I was just a little bit confused and I didn't want to dive too deep down that hole, but it was interesting.
I see, great. I have the other questions probably more toward discussion, but before I dive in, do we have time, or perhaps other people have questions? I don't want to use.
I'll stop sharing if anybody, unless anybody has any other questions on this.
Yeah, let's see if anybody else has any specific questions for this module for David or for me, and then we can go to discussion. So that's going once, going twice, going 3 times. Go for it.
Go for it.
Yep.
Oh, cool. So very nice presentation for both of you. Thank you so much. I learned a lot. And the discussion that I have in mind is that it's probably related to the first example that we use Yelp reviews and try to use the phrase matcher to figure out, okay, what dish, and use that to get a score. So the underlying assumption for this approach is that, say, whatever dishes that been mentioned in that review would be associated with one fixed rating. I think we discussed that previously, and there's drawbacks such as, okay, in a particular review, they might like one dishes but dislike the other two, or previously mentioned, they give it low star number. Perhaps it's not because of the food. They could say, I love this food, these are the dish I ordered, but I don't like this service. And so my question is more related to when I say, if I present this result to the restaurant owner, so this is what I found, and he or she challenged my approach by this, say, how do you know, have you considered this, such as the two scenario that I mentioned? Do we have, so unlike like the other example that that one of the presenter provided, we can compare with ground truth. Like, okay, there's a label that we can compare to and give an accuracy about our model. But in the first example, is there a way to know how accurate our result is? Or if the restaurant owner is challenging our approach, we could say, hey, with our approach, if you are worried about this scenario, we have disregard this entry in our model, or we have a way to test, okay, in the extreme scenario, this will be the predicting results. I wonder whether you have any comments or discussions on that regard.
For the, if this review is pertained or is related to the item or the restaurant, this analysis is not enough, I would say. I would say we need to dig a little bit deeper and actually have a category about maybe staff or restaurant or how clean the place was or parking or whatever other categories we think are important. We basically need new keys for that. The issue that if a person gives or mentions multiple items but only gives one review, that we might need a little bit more advanced techniques to really identify which part of the review or which sentence made him choose those 5 stars. I don't think with this approach we'll be able to figure out that the 5 stars are due to the sandwich or the 5 stars are due to the staff, but the food was a 3. Like, curious what you think, David.
Yeah, I agree. Like I said before, this is purely data analysis, and it's very important the way it's presented. So, you know, as you went to the restaurant owner or whatever, you would say, you know, very clearly, this is a, you know, an average rating out of 10 reviews that mentioned chicken cutlet.
I'm curious now about the chicken
had
cutlet.
an average rating of this, you know, value, whatever it is, right? So you got to be careful about what you're giving them, that they understand clearly.
I see, thank you. And it seems like it's difficult to find a ground truth about, say, I heard that we propose another approach, say, like have a more granular, identifying the staff at the staff level or other level, and we assume this approach is better, and we presented that results. But again, we don't have a ground truth to compare with, and when people challenge us, how do you know this result is actually better than the other results?
When you mean other results, what do you mean?
So right now I heard we have another approach. Okay, you don't like this approach, that's fine. Let's do it more granularly. And with this approach, we're supposed to get a more accurate results.
Mhm.
But when I've been asked, okay, how do you prove it? How do you know it's supposed to be better, but do you have a solid evidence to show that it's actually better? So compared to the second example, we have ground truth to compare with.
Mhm.
So we could know, okay, this model is more accurate than the other model. But in the first example, I try to figure out whether there is such a ground truth that we can reference to.
Yeah, I know what you mean. So the signal to noise ratio, to me, that's what it looks like. So here we have a lot of information, but this review that we're looking at, we're not sure exactly if it's due to an item or the staff, or the waiting time or the payment methodology. Like that quality of label is not as good as in the other examples that we saw, where it was clear the sentiment, it was positive or negative. I think we need more advanced techniques here, right? We need like more modern techniques to figure out that due to this sentence, specifically due to this sentence, that's why the review is 4. And that has been shown to me to be more accurate from other data sets, not necessarily Yelp.
Are all these reviews true reviews, or could be fake reviews, some of them?
That's a good question.
Another thing you can predict.
That I don't know. What can you trust online?
I mean, if you want to get like model accuracy, and you know, which we're not talking about here, we're just talking about data analysis, right? We're just reporting these are the facts, right? So you got to say it the way it is. This is what the data is. This is not a prediction. But if you wanted to do prediction, then you do need, you know, you've got to do some kind of labels, you've got to do some kind of, you know, supervised learning, or you've got to do some technique to do semi-supervised or unsupervised learning, right? So, and we're definitely not doing that here yet.
In the upcoming LP course, though, we can revisit this Yelp review, right, Robert? And we can see if we can take a deeper look.
For sure.
If the 5 stars, if the chicken cutlet is actually bad, or maybe the machine was broken there and nobody could pay on that day. Maybe the chicken cutlet is fine. And just our payment system sucked.
Well, I had date in there, and I think that would be an interesting thing to have.
Oh yeah,
in the data too, right? Like,
Suppose the chicken cutlet was only offered during the one summer when the air conditioning went out.
Right, food chicken cutlet. Like whoever came up with that menu, like, come on, it was their favorite recipe. Turkey sandwich. That looks pretty good to me.
But it's an Italian restaurant, right? And I think in America we typically expect that if there's any cultural significance in the classification of restaurant, that the establishment will stick within a certain set of bounds.
Oh,
right.
Or that's what many customers expect anyway.
You don't expect a lot of exotic items, right? You expect classical, typical Italian items, right? So if you see something that is not Italian, then you might not go, you mean? Or you might not give it a good review?
I mean, there's something to be said for specialization, right?
True. I don't know if we asked if we answered your question, Obi, but that's a good question. How can we make sure that our analysis basically answers the questions a little bit better? We need a deeper look, I'd say, and a more advanced approach. I was looking at the code here, switching gears real quick, of this text categorizer. And if you remembered, we had the different architectures. We had a bow, a bag of words, a simple CNN, or the ensemble one. And for this build bold text classifier, I think that's what I was looking at. I found it somewhere here. I don't know if anybody can tell here what's going on, but you have a class, ngram size 1, exclusive classes false, a layout layer false, and some extra arguments. Model define operators, chain, with CPU, extract ngrams. And what is this operator? I mean, I've only used this in maybe like bitwise, but I don't know. Has anybody used this operator before in Python? Like, I don't really understand this, but somehow maybe this is the input into this linear model. I don't know. Same here. Model XOR maybe, or bitwise.
Looks like they're trying to use it to chain models together. Like somehow they've overloaded that operator right there.
Got it. Define operator. Got it.
I mean, I'm just guessing, but maybe they're chaining one and building a pipeline that way.
So you're doing something, and then the output of that is fed to this model.
Right.
Got it. Oh, interesting. Okay.
That's just a guess.
I haven't come across this before, so I was curious. And then this linear model, I don't know if it's defined here. From think linear model, import linear model. Okay. And the other thing we wanted to look at was, I don't know if it's here though, the average. I'll look at it offline, and maybe I'll post it on Slack if I find anything about the averaging of going from 12,300 to 1,300, going from like multiple words to one vector representing the entire document.
Yeah, I just looked at the documentation for similarity, and the language of it seemed to imply that there might be other averaging methods, but nothing was actually shown.
Oh, I see.
Like there might be other keyword arguments that only certain people know about.
Quick question, David, Robert, do you use SVMs a lot as support vector machines? This is the first time I think that we come across them in Kaggle courses.
I do not.
I think it's more likely to come across them academically than to actually use them.
Because in that data set, it retrieved what, 93%, right? And random forest couldn't beat it, right? Maybe a deep learning model could beat it, right, David?
I just looked up that operator. It's either normally it's for like a bitwise right shift or for an output file of redirection, but I guess it must be overloaded, as you said, in this case.
Define operator, yeah.
Changing.
Oh boy. Overloading to the extreme. All right, cool.
You run out of symbols, so you got to reuse them.
Oh, it seems like the dot notation with one thing dot after the other works pretty well for piping.
Right. Yep.
That's the standard approach in Python anyway.
And then I wanted to look at these gardens in San Francisco where the atmosphere was interesting, and that's apparently a garden, right? Not only that, but I think this was the original name of San Francisco. If you Google for that name.
It's also the name of the still existing island in the middle of the bay.
Oh, really?
The Bay Bridge crosses over an island halfway between San Francisco and Oakland, and it's Yerba Buena Island.
But I love it. This is the original picture of San Francisco, Yerba Buena. I was like, okay, cool. I'm learning something new. 1848.
I just saw this video that this neurologist guy was basically saying that today's children are going to be so much smarter than us because they have instant access to information all the time, and like that's really good for learning. Like the minute you think of something in your head and you want to know something, if you don't have to wait to remember to get the answer later, you just look it up right away, and it's like the context is already in your mind, and it's like you learn it. So like what you just did there, it's like.
I came across it, I looked it up, and I saved it. But I don't know if instant access to information make you smarter.
Maybe not smarter, but maybe not more intelligent. But they'll just, I don't know.
Maybe too.
Know a lot of stuff. Facts, useless facts, maybe.
I don't know about that. We'll see. Cool. Any other questions, comments, feedback? Otherwise, we can wrap it up here. Yeah, I love this. This was a very interesting discussion, and it was using a new set of tools that we hadn't come across. So that was very, very interesting. Thank you.
Thanks very much. It was really nice presentations.
Yeah, I loved it. Yeah, feel free to join us then. We have a few more sessions coming up. Next Wednesday, we're doing another micro challenge. We didn't get the time to do it last time. This is on airline price optimization. If you're interested in that kind of approach, I think, or it will use something called dynamic programming. If you've come across that, that's a very interesting approach in optimization. Then we have our get together for holidays for Christmas. I'm trying hard to make these are not my guinea pigs. I'm trying hard to make my guinea pigs look like that. I ordered them some cute Christmas hats and Christmas decorations. And hopefully they'll look as cute as that.
Oh, those weren't yours?
No, there's no way I can make mine stand like that for more than 1 second.
Those were models.
This is the training set for the labels to build a model to make them look like that. Hopefully next time I'll try. Then on January, we'll take a break mid December or December 23rd. We'll take a break, and we have 2 more sessions, one on computer vision, another one on reinforcement learning. And then that will wrap up our Kaggle adventure. After that, we might do a single session on logistic regression and decision trees, just a quick wrap up on that. After that, end of January, I have a surprise for us. It's still a surprise. I'm trying hard to make it work, but you'll see it. It should be fun, end of January. And that will wrap up our Kaggle adventure, and we'll go on to the next one. Cool. With that said, let me stop sharing. I want to thank everyone for joining us. This was a fun discussion, and hope to see you next time. And I'll stop recording here.